In the last video, I ended with this question. How does t of n, the running time of an algorithm, change if n doubles? So let's go back to our sequential search algorithm. And what do we have? We have this expression for the running time. So this is the worst case running time for sequential search as a function of the length of the input array. So this expression, we worked it out, and it's n times a plus b, where a and b are system specific, are constants. So they're constants that are specific to my system. And so because they're specific to my system, if I answer this question for my system and give you a number, that'll be less useful than if I can answer it in a system agnostic way, or a universal way. All right, so here's a way we can get at the answer to this question. What happens if the input size doubles? All right, so let's compute the following ratio. Let's compute TSSW of 2n over TSSW of n. Right. Now, what is this ratio? This ratio is just going to tell us how much more the input, or how much more the running time changes when I increase the input size to the size to 2n as opposed to just n. Okay, so here's the first piece of the question. The second piece of this question that I want to ask is a little bit more nuanced. It says, suppose I want to take this ratio and I also want to make n large. So I'm going to do this. I'm going to ask, what is the limit as n goes to infinity of this ratio? And what I hope to obtain is some universal fact about this algorithm that tells me what happens when the input size doubles. Right? So let's see if it gives us that. So we have this expression, so I'm just going to drop this down in here with 2n replaced into the top and just n replaced into the bottom. So this is the limit as n approaches infinity of TSSW of, nope, sorry, that's done. So this is 2n times a plus b over n a plus b. Okay, so now you've got to dig back to some calculus knowledge, and you'll have lots of practice doing that in this class. And think about, how do you compute a limit? Well, one thing we can begin by doing is we can separate this into two different terms. Right? So this isn't even calculus yet. This is just algebra. So I can say, what's the limit as n approaches infinity of 2na over na plus b, plus the limit as n approaches infinity of b over na plus b. And now there's one really easy simplification we can do, right? So take a look at this second term here. What happens in this term when n gets very, very large? Well, when n gets very, very large, the denominator here gets very, very large. So you have something that's constant. So it's constant in n, divided by something that's very large. So what do we get in the end? Well, as the larger n gets, the smaller this thing gets, and there's no lower limit other than 0. So this whole piece is 0. Okay. So now I can just focus on the first piece, and let me do something to the first piece. Let me manipulate it in a particular way. So first, I'm going to notice that I have a 2 that's multiplied onto the first piece. And if you remember back to your calculus knowledge, you can always take that 2 and pull it out of the limit, right? It's a constant, doesn't matter, so I can just take it out. So first, let me take the 2 out. So this is 2 times the limit as n approaches infinity of some stuff. So now let me divide both the top and the bottom by n. So I'll end up with a on top divided by a on the bottom plus b over n. So now you're saying, Brown, where are you going with this? Well, now look what I've done. Now see what happens to this expression when n gets very, very large. right? So in the previous line, what we said is when n gets large, if n's in the denominator, then that fraction goes to 0. So what do we have? We have a fraction with n in the denominator. So this particular piece is going to go to 0. And this whole limit will converge, and so then we don't have any n's anymore once that goes to 0. So this whole limit ends up at 2 times the limit of a divided by a, the limit as n approaches infinity of a over a. Well, there's no n's in here, so the limit is, this is all constant in n, so there's no n's whatsoever. So this, and the a's cancel, so this just ends up simplifying to 2. Okay, so what were we doing? We were trying to understand how sensitive is this piece, how sensitive is the running time of this algorithm to changes in n, and we asked the question in a way that made all these constants go away. Right? So what's important about this question is that it's system independent, right? Because we asked the question in this particular way, we got an answer that is true on my machine, it's true on your machine, it's true on a mechanical adding machine, it's true in a universal sense, right? So here's the big takeaway. So the answer is, if the input size doubles, the running time about doubles, and the answer is totally system independent. Right? And we might use the word universal. I like the word universal. Or even fundamental, right? Fundamental is another fun, grandiose word that we get to throw around in this class. And it's universal in the sense that it's a true statement that depends only on the mathematics of the algorithm and has nothing at all to do with the system that it's running on. And so this is always going to be the focus of this course. In all of the analytical work that we do, whenever we are actually designing and analyzing an algorithm, we're never going to ask how long does this thing take in seconds. We're going to ask a question like what I just asked, not identical to what I just asked, but like what I just asked, that gets at this property of how is this algorithm, how well does this algorithm perform in some universal way. And so this will take us in the coming days into the language of big O and big omega and asymptotic guarantees and things like this. But fundamentally, this is the reason that the questions in this class are interesting, because they are universal. Right? That's what makes these good questions to ask.